Let's continue to talk about electromagnetic radiation. If we take an electric arc and run it through a prism, what we see is a continuous spectrum because all wavelengths of light are produced by the electrical arc that gives off white light. So if we look at this, we have red, orange, yellow, green, blue, indigo, and violet going from long wavelength red to short wavelength violet. Red is the lowest energy form of visible light. Violet is the highest energy form of visible light. If instead of an arc, we take high voltage and pass it through a tube containing hydrogen gas, we get a much different emission spectrum. We get a line spectrum where each line corresponds to a discrete wavelength of light. With hydrogen, we don't get a continuous spectrum of visible wavelengths. We get discrete wavelengths of light. We get 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometer wavelengths of light. This is significant in that we only see certain energies are allowed for electrons in the hydrogen atom. Here, the energy of the electrons in the hydrogen atom is quantized. Niels Bohr further elaborated on the line spectrum of hydrogen using knowledge of angular momentum from classical physics. Bohr gave hydrogen atoms energy levels consistent with the spectrum and developed an equation for energy levels available to electrons in the hydrogen atom. In the Bohr model, the electron in a hydrogen atom moves around the nucleus only in certain allowed circular orbits. Bohr's model gave hydrogen atom energy levels consistent with the hydrogen emission spectrum. The ground state, or the lowest possible energy state, was assigned n equals 1. Here is an energy level diagram typical for electronic transitions. We can see the n equals 1 ground state at the bottom of our energy level diagram, and excited states n equals 2, 3, 4, and 5 above at higher energy than n equals 1. Notice that the line spacing between n equals 1 and n equals 2 is very large, and as we go from n equals 2 to n equals 3, n equals 3 to n equals 4, and n equals 4 to n equals 5, the spacing between energy levels becomes smaller and smaller. If we treat the electron as circular orbits in the Bohr model, then we can begin to assign the wavelengths seen in the line spectrum to transitions in the Bohr model. We can see the transition from n equals 2 to n equals 1 gives off our red wavelength of light. Our transition from n equals 3 to n equals 1 gives off our green. And our larger transition is going to give off our higher energy wavelengths of light. For a single electron transition from one energy level to another, the change in energy is equal to minus 2.178 times 10 to the minus 18 joules times the atomic number, which is Z of 1 for hydrogen, over n squared final minus the Z squared value, 1 for hydrogen, over n squared initial. The delta E here is the change in energy of the atom, or the energy of the emitted photon. N final is an integer, which is the final distance from the nucleus, and initial is an integer, which represents the initial distance from the nucleus. The Bohr model correctly fits the quantized energy levels of the hydrogen atom and postulates only certain allowed circular orbits for the electron in the hydrogen atom. As the electron becomes more tightly bound, its energy becomes more negative relative to the zero energy reference state. As the electron is brought closer to the nucleus, energy is released from the system. Now it's important to note that Bohr's model is incorrect. This model only works for hydrogen, because in hydrogen the electron moves around the nucleus in circular orbits. For other elements, we do not necessarily have circular orbits. It becomes a much more complicated situation.